Hi, everybody. So, what we have today is continuing to look at circuits, and I wanted to start to get us toward actually being able to calculate things with circuits and to look at the equations that we have on our reference table. And so you want to notice first and foremost that there are two sets of equations for circuits. One is for series circuits, and as you've seen in our previous things, a series circuit is just a circuit like this one here on the left, where the electricity only has one path that it can follow around the circuit. And so when we do this switch, you see that the electricity will go up and through each of these light bulbs. So you see how slowly this is going. Having the three light bulbs or three resistors in a series like this is going to provide a lot of resistance to the circuit. It's all the resistance of these three light bulbs added together is going to be the total resistance across this circuit. And you'll notice that in the equations when we look at them. However, if we go over here to a parallel circuit that still has three of the same exact type of light bulbs, the same exact resistors, you'll notice right away the difference of what happens when they're wired in parallel. Now, you notice, of course, that these are much, much brighter, but also notice that the electricity is moving much faster in the overall circuit. It's much faster here, and then it's moving slowly through this first one. It's moving slowly through the second one. It's moving slowly through the third one. But then it all comes back together, and it's very fast through the battery. So you'll notice we're having all three of these be the same brightness when they're in parallel, but also that we're really using more energy from this battery. It's very interesting. Now this is part of your reference table, and you can see that this is where we have our series circuit equations and our parallel circuit equations. The most important thing about actually calculating current, voltage, and resistance in these different types of circuits is starting out by thinking about what type of circuit you have. If you have a series circuit, you have to use these equations. And if you have a parallel circuit, you have to use those equations. And we want to talk quickly about what these different equations are going to do for you. If you're in a series circuits, then the first thing you want to notice is that the overall current in the circuit is the same as current number one, that maybe you measure the current with an ammeter before it goes through the first light or through the first resistor. And it's the same, it's equal to current number two, it's equal to current number three. What this first equation means is that the current is the same everywhere in the series circuit. And that should really make a lot of sense, that the current would be the same no matter where you measure it, because you only have one path in a series circuit for the current to follow. In the same way, notice that the voltage is not the same across each of the different places that you could measure voltage. The big V right here is the voltage across the battery. So when you read on the battery, it says that it's a 9-volt battery or a 4-volt battery or something. That's the reading on the battery. So the overall circuit has that as its total voltage, its total potential difference across the full circuit. But if you measure the voltage across just one light, it would be V1, or the voltage across another light would be V2, voltage across the third light, V3, and so on. You would have to add up all of those potential drops across your lights. And when you add them up, that's the total voltage, maybe the reading on your light bulb. And that's because there's, again, only one path. So the total potential drop is just going to be the sum of all of the little drops in the series as you go across. And it works the same way for total resistance or equivalent resistance of the circuit. You're going to add the resistance of each of your light bulbs or each of your resistors together. Now, it's very different in the situation of a parallel circuit. In a parallel circuit, if we go first down here to the voltage, you'll notice in this one, the total voltage is the same as the voltage across the first light bulb, and it's the same as the voltage across the second and the third light bulbs. All the voltages, no matter where you measure the voltage across the resistor or across the entire circuit, it's going to be the same because each of these voltages represents one of the many paths that you can take through this circuit. And so no matter which way you go through the circuit, it's going to give you the same amount of voltage. If we go up here to the current, because again there are many paths, the current across each path, added all up together, the sum of all the currents across the paths equals the total current that you have for the overall circuit. So this current is like if you measured the current with an ammeter right next to the battery, you would get the total current. And each of these currents are measured just across the path, across those parallel paths. And now your resistance is a much more complicated way of figuring out, and you would have to use a little bit of algebra to solve this if you knew the resistance across the different light bulbs, and then you had to solve for the equivalent resistance. But in general, what happens here mathematically, and we can see this in some examples, is that the more paths you add, the lower the equivalent resistance. So even if I add another path that has a very high resistance, it's actually still going to make the equivalent resistance of the overall parallel circuit go down because I've added another path, and some electrons are going to take that path, which means the equivalent resistance of the overall circuit is going to go down the more paths that I have. So let's look at some example questions. And that way it'll help you really flesh out how to use all these different equations in your different situations.
So here's a question involving series circuits. Imagine that we had a series circuit with three resistors. We're going to call them R1, R2, and R3. You could imagine those being three light bulbs, or you could just imagine them being three little resistors. Either way, it works the same. So when we draw this circuit, we're going to have a 4-volt battery in this question. And I'm just going to draw my light bulbs in a simple little way with the squiggles. But notice in my series circuit, I only have one path for the electrons to flow through. So there's one path, but there's three resistors to go through. If you look back at your reference table, the way that the total resistance or the equivalent resistance for a series circuit operates is that we have the equivalent resistance equals the three resistances that we have added together. So all I need to do to find the equivalent resistance of the circuit is to say that's 1 ohm plus 2 ohms plus 3 ohms, which is a total of 6 ohms of resistance. Now, if I know the total voltage of my battery, and I know the total resistance across the entire circuit, I can put those values in to my equation, Ohm's law, and I can find the total current going through this series circuit. The reason that the current going through, imagine if I put an ammeter right here, I could measure the total current going around this circuit, or if I put the ammeter here, it would measure the total current going through the circuit. Ammeter here, here, here. No matter where I put an ammeter to measure the current going through this circuit, it's going to measure this value, which is the same as the total current going through the circuit. And the way that I can find that is by just plugging in these numbers, dividing on both sides, and I should get a current of 2/3 of an amp. So notice that there's 2/3 of an amp of current going around this circuit when I have these three specific resistors in series. So now let's look at an example of a parallel circuit with the same information. Imagine that I had the same 4-volt battery as before, And I wired this in parallel to resistors R1, R2, and R3. So I'm having the same amount of ohms of resistance as our previous example. Now, we still have the same equation, Ohm's law, which is going to govern the overall equivalent resistance of the circuit, the overall voltage, which is our 4 volts, and the current. And that current is the current going through the overall circuit down here. But notice it's very easy to see, since there are multiple paths that that current can take, the current is going to be different if I measured right next to any of these resistors, because it's not getting the total current, and that's very, very important. So in this example, I'm going to go through it a little bit of a different way. Maybe we'll see two different possible ways to go through this, because the first way is a little bit harder. If we again try to find the equivalent resistance of this circuit first, you'll recall that from the reference table, the equivalent resistance for a parallel circuit is a much more complicated equation, where the resistances are in the bottoms of the fractions, and we'd have to go through and very carefully calculate that out. Now, I'm going to do that for you once, but I would like to make sure that I show you there's a simpler way to go about this. And the simpler way is to remember that the voltage across the entire parallel circuit here, that 4 volts, is going to be the same across each and every path. And so if we start with this concept, we now know that this is 4 volts across this lamp. It's 4 volts across this lamp and 4 volts across this lamp. And we can use our Ohm's law equation across each lamp individually, because we know the resistance and we know the voltage across each of those lamps. And it makes the calculations much, much simpler. So for instance, if I were to look down here, let's call this resistor number 1, all I would need to do is V equals IR. I can put in the 4 volts. I can say I don't know the current going through resistor 1, but I do know that it only has 1 ohm of resistance, and I can very easily find that current. The current, when I divide by 1 on both sides, is just going to be 4 amps going through this first resistor. And in the same way, we can find the current going through the other two. If we do some quick calculations, we should get, here we're going to have 2 amps, and here we're going to have 4/3 amps. And you can check that if you pause the video and check those calculations to see that those come out correctly. Now, once we know the current across each path, we could, of course, find the total current that we had talked about down here. Once we know the total current, we could find the total resistance. And that way, each calculation is a little bit simpler. If you go through and find the total resistance immediately from these values, and you do 1 over the equivalent resistance equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. You notice that there's a lot of fractions involved to add together. You end up having to do kind of some cross multiply and divide, some algebra work to solve at the end. But when it's all said and done, and you can try this as an exercise, it's good to practice with fractions, you get an equivalent resistance of 6/11 of an ohm. Now, if you compare that amount, the interesting thing here is to compare that amount, 6/11 of an ohm, to our series circuit, where we had a total of 6 ohms of resistance for the circuit. This one only has 6/11 of an ohm, less than 1 ohm of resistance in this parallel circuit. It's much, much less. And so we could calculate that and then find the total current, and that would be fine too. So I would recommend that you go through each of these two questions And make sure that the calculations using the equations on the reference table really make sense to you with these examples. And let me know in the comments if you have any further questions about this before I give you Regents level questions to try.